Hello everyone, today we will be proving some trigonometric identities. Today we will be mainly discussing geometric proofs for cosine and sine. I will not be doing tangent as that can be derived algebraically just by dividing the two. So the first one we will talk about is the compound angle identity for sine. So one thing to keep in mind is that if I have a plus here, the only other plus or minus sign in the equation it will be the same, unlike the cosine identity. So it can just be written as sine x cosine y plus or minus sine y cosine x. Note that the structure is the same, you just switch the x and y between the two parts of the equation. So the most common way to prove this is to use two triangles and to join them together with a rectangle. My apologies for the drawing. All right. So let's consider this one to be x, this angle, and this angle to be y. So the smart way of doing this, and there can be many different proofs. I'm going to try to use different geometric forms for each proof just to give more variety in case one is forgotten on the test. So the thing to consider is that we want to, in every proof, we usually want to set one of these sides to 1. Of course, this can still work for any number. We just want to make it simpler for the proof. So the side we're gonna set to 1 will be this side. This is just so that usually we want the hypotenuse to be 1 because any sine or cosine function will always be one side divided by the hypotenuse. So we want to put that as 1 just to keep it simple. Of course, if you can scale it up by any factor, so this works for any number. So the first thing to notice is that we want to get the main equation sine. Let's just do the positive one for now, because the negative can just be substituted in anyways. So this is angle sine x plus y, so this is x plus y, and taking the sine will just be this side divided by this side. So it's just the opposite side of the angle divided by the hypotenuse. So considering that we want this height, this diagram is drawn in a way so that we can have basically two ways to get this height. So the first way is just this entire thing, or we can split it off here and take this part and combine it with this part to form the major part. So if you want my personal opinion on how to draw this best, I would say to start with this triangle, as just in my opinion, it's the hardest part to memorize, as you want the right angle to be to actually look like a right angle. If you start with these two, it can be hard to get the right angle right. So that's what I would recommend, and there's the most intersection lines in this triangle. So, as stated earlier, this is our indirect way to form this major chord, this major length. So, when I first look at this triangle, and I'll try to do it from a way where I don't know exactly what to do yet. So in the case of a test, you can also just use your thought process to arrive at the conclusion, because I think it's fairly simple just if you already have this diagram. So when I first look at this triangle, this is the length I want to start with. This one seems harder to find as there's no direct way to just really get it just with this x, while there is a way with this y. So to this angle would be easier with sine of y, because cosine would take this length and this one gets ignored. So let's first take the sine of y, and the sine of y, let's just say this is a and this is b for now, equals to a over b. So what we need here the most would be b, as we already know what a is. A is the part of the major chord that we want. So how do we get b? Well, when I think of this, I want to find a way to get a ratio of this and another object, so b over something, and then we want to multiply that by the something. So in order to do this, we want to get a ratio. So the only thing that we can do to produce a trigonometric expression that results in a ratio with b as the numerator will be cosine of x. So notice here that we already set this side to 1. As stated earlier, you can set it to any number and just have them multiplied in front. So this is why we wanted to make it 1, because if we just divide b by 1, it's just b. So we can find that this side, b, is just cosine of x. Now if we substitute that right here, we can derive a just by multiplying both sides of the equation by cosine of x. So if you notice, this is already one part of the equation that we have. So now we have to find a way to derive the smaller length. So let's just keep this somewhere. Alright, so the next step, intrinsically, we want to find a ratio of this length with something. So the best thing we can do right now will be something like taking the sine of this angle, where we can get a ratio with this and that. Of course, we can also get tangent, but that doesn't really do anything, as there's no way for another angle to cover this. So we don't have neither x or y can directly take a ratio of this. So what we want is to find a length that x and y can make a ratio of when a trig function is applied. So for now, let's take this side, and like the other attempt, let's just set this to z. And like the other one, we can get this d through this x again. So as earlier, what we described, we want to find a way to find a ratio of this length through x. And of course, the easiest way is just to get the hypotenuse again. So what we want to do is we want to replace d with this value, so sine of this will just be sine of x, as once again, sine, when you divide it by 1, nothing happens. So this one will equal sine x times sine z. Now what I did is that I intentionally chose the wrong angle to do this with. And I will show through this process how this can be achieved. So this z angle we want to derive. This angle is equal to 90 minus x. As in a triangle, we have 180 degrees. We want to subtract this 90 degrees, and that makes it 90. And just to get this last angle, we subtract x. So we only want this part of it, so we have to find this part. And to find this part, what we want to do is we want to use 90 minus this part. So 90 minus x plus y, and then this whole thing is subtracted from 90 minus x. So let's just simplify this a bit. So 90 minus x minus 90 minus x minus y, and this turns into 90 minus 90 plus x minus x plus y. So note that these two cancel, and we are just left with y. So let's continue. We now know that this angle right here, this angle right here, oh, that's a bad color to use. This angle right here is equal to y. So z, as said before with the right angle, z equals 90 minus y. So using that, let's put this back into the equation. So c equals sine x times sine 90 minus y. I'm kind of running out of space here. I'll write this next one a bit smaller. So some of you might already know that this will equal cosine of y, either from the equation or from previous knowledge. However, it is always good to think about why necessarily it does. So let's consider an angle y, and I'll use another different color for this. So what we have is 90 minus this angle. So 90 degrees is this line right here. So we want to subtract y degrees. So we are shifted this way by y degrees. So let's once again draw some angles. So this degree right here is 90 minus y. So as always, what we want to do is we want to set the hypotenuse to 1. Just in this case, it works really well. So what we want to do is we want to find, let's just derive sine of y first. Sine of y will be this side divided by 1. So this is sine y. And let's get sine of 90 minus y. So sine of 90 minus y is this side divided by this side. So this is sine 90 minus y. So notice how sine y does not equal sine 90 minus y. This will not work, and thus we want to find a different way to represent sine 90 minus y. So thinking of another angle, just like this earlier problem, we want to find an indirect way to add up two different sides to equal the side that we want. So what we want is this side. Well, instead of doing two different sides, we can just use this side. Once again, we want a ratio with this side and another side. And since we already have this side, the hypotenuse is 1, we can get that cosine of y. So this is this divided by 1 is also equal to this side. So that's sine 90 minus y. So if we come back to this problem, we can substitute cosine of y. And that is our final answer. So combining these two, that's the wrong one. Combining these two, a plus c, we can finally get sine x plus y, which is just this side over 1, which is at the end just sine x plus y. So that is how we get the angle, compound angle identity for sine, and just put these two back into the equation. So what we can learn from this is that you should not be intimidated if you don't have the entire proof memorized. Even if you just look at the picture and go through every step, finding every ratio, trying to find a way to represent everything just in terms of x and y, you can prove the identity. Even if you do choose the wrong side to do your equation, or you have something difficult, you can simply just think about it or go back to your past knowledge. Always remember that one of the most important things in math is to find indirect ways of getting something that you want. So for the next few identities, we're going to go a bit faster, as we're not going to necessarily find a roundabout way or just a different, more extensive method. So this time we're going to do cosine x plus y. So what is important to consider is that this is two sines, and this is followed by two cosines, and the addition sign always is flipped. So when this side is positive, this is minus. When this sign is minus, this one's positive. This one's a plus. So the x and y's stay consistent. And yeah, so this one I think is an easier method compared to the first one. You simply just have a square. Oh, actually, let me make this a bit more straight. My apologies. All right, so we want 1 point here and 1 point here. Oops, did that not register? Now, I think this one's easier because, as described earlier, just the diagram is the hardest part. The actual proof is fairly intuitive. Compared to the last one, this one you just need to memorize the wavy or just the angled triangle, and it's just a box instead of other lines going around it. You can use this for other functions, but the easiest one to derive from this would be cosine, in my opinion. So let's set angles x here, y. Oh no, let me actually make this smaller. And as always, let's set the hypotenuse to, so let's set the hypotenuse of the triangle to 1. Now obviously this is 90 degrees, and let's start. Note that there are 3 common angle letters, I guess, for when there are parallel lines. So let me make them a bit more obvious. So consider that I have 2 parallel lines. There are 2 ways. There are 3 ways to or letters to memorize. So we have the Z, we have the F, and we have the C. So what we want to memorize is that the 2 angles of the Z are always equal to each other. The 2 angles of the C make up 90 degrees. So if this is x, this is 90 minus x. And for the F, we just want to memorize these 2 are the same. And yeah. So from this, if we take a look, these are actually 2 parallel lines. So if you notice, there are 2 shapes that we can make right now. We can make the C and we can make the Z. So the Z is what we want right now. So if you remember, this angle is always equal to this angle. So that means that this angle is also x plus y. Let's continue. This one will be 90 minus x plus y. Oh, and 90 minus x plus y if you don't break the brackets. It will be 90 minus x minus y if you do. This one we don't really need to use, but I will just show all the angles. This one will be 90 minus y. And since this is 90, this is 180. This means that these 2 add up to 90. So 90 minus y produces y. And this is 90 minus y. So this one's what we really want to consider, but on a test you can just get all of them in case you don't really memorize which 2 are important. So I will rewrite these in red just to make them seem more important. So the first thing we want to do, this seems just like last time, we want to get sine, or this time's cosine of the main 2 components, which is x plus y. So notice that this notice that this side, no matter where you look, there's no right triangle that contains the opposite of this angle. And we need to be extended upwards for you to get it. So instead, as we did earlier, we can use this angle. So cosine of this will be the adjacent side, which is let's just label this z for now. So let's do z. Oops, my bad. So cosine x plus y. So z, and then we're dividing it by the hypotenuse. So as always, since this is 1, it's just equal to z. So let's substitute. Oops, why is it so big? Let's substitute it. So as last time, we have two lengths that are equal, and we want to find a roundabout way to represent this length this time. So what we do, we take the large length and we minus the small length, and then we get cosine x plus y. So let's start with that. So let's start with this side. So let's name this A. Oops, let's name this A. Let's name this B. Note that getting this will use tan, and is fairly redundant. So we can take the cosine of y to get a ratio for this length. So cosine y equals a over b, and we want to move b to the other side. So b cos y equals a. Now to find b, we want to find a ratio, and we're going to use the hypotenuse as always. So this one will be cosine of x will give us b divided by 1. So this side is equal to cosine of x. So cosine x, cosine y equals a. So this side, let's label it. And let's continue. Now we want this side. So this sign, we can use sine of this and get divided by this. So let's name this c. My bad. Let's name this c and name this d. So sine y equals c over d. We want to bring d to the other side. D sine y equals c. D, once again, we use this x, and then we take the sine of this x, so we get d over 1. D over 1 is just d, so we can substitute sine x, sine y for c. So as you can see, we have the main length, we have this length, we just subtract the two. So cosine x plus y equals to cos x. Oh, let me put that on the new line actually. Cos x cos y minus sine x. Oh my god, x sine y. So that is our final answer. So now let's move on to what else? We have sine 2x equals 2 sine x, 2 sine x cosine x. This one, we can just use sine x plus x. And since this is not geometric, I'm just going to glaze over it. But as we've seen earlier, this is just sine x cosine x plus sine x cosine x. So and it's just two of them. And you can do this for cosine of 2x2, which equals this. And the other two are actually, let's just do it really quickly. So cosine 2x equals 2 cosine x plus x. So cosine x times cosine x minus sine x times sine x. So this is just cosine squared x minus sine squared x. And note that sine squared plus cosine squared equals to 1. And this can be proved really quickly. Imagine this is x. Sine x is this side. Since it's divided by 1, it's just sine x. This one's cosine x. Squaring both sides, we get the Pythagorean's theorem ABC. So this squared plus this squared equals to 1 squared. So it's just equal to 1. And let's continue. So we can move sine squared to the other side. And then we put that in here. So let's see, 1 minus 2 sine squared x. So that's the second solution for the problem. We can also move cosine to the other side. And doing so, we will get sine squared x equal, oh, I forgot the x is here. Sine squared x will equal to 1 minus cosine squared x. We substitute that there, make it negative. So this turns into plus, this turns into minus. So cosine squared of x, and there's 2 of them. So we put a 2. And then we, let's see, minus 1. Is that right? Yes, minus 1. And that is our third solution. So let's continue with the cosine and sine laws. Alright, so let's get started on the cosine law formula, my bad. So we have C, let's just do C for now. I'll show you why the square root should make sense. So this will be a squared plus b squared minus 2ab cosine, that's why it's called the cosine law, of, let's just say gamma, because when you put the cosine law into Google, there's a calculator, and then they make it look like this, and it's so fancy. But I'll tell you why C is important, why it's usually in the form of C and not A or B. And that's because of the Pythagorean theorem. Usually C is isolated, so putting C by itself here just makes it look a bit better, I guess. So the triangle we're going to be drawing for this will just consist of one right angle triangle, which makes it easier. And in the middle, we're just going to split a line down. This doesn't have to be perfect. It's just a random line. So let's put A here, B here, and C here. Now, if you paid attention to the foreshadowing, we are going to use the Pythagorean's theorem, meaning what we want is this side, this side to the power of 2 plus this side to the power of 2, and then we get C squared. So let's get this side, and let's put gamma. Gamma is always the opposite side of C. So gamma is here. So this is 180 degrees minus gamma. And this one is 90 minus 180. Oh, I don't know what I'm doing. 180 minus y, and that's in brackets. So this will turn into positive y minus 90 degrees. Oh, and in the video, I don't really say degrees, but all the numbers that look like they should be degrees are probably degrees. So let's set this to, it's gamma, not y. So gamma, gamma minus 90 degrees. So to get this length, what we can do is get a ratio of this side and a variable that is in the equation. So getting this side won't really do anything, so we want this side, so the hypotenuse. So as before, and this is cosine gamma minus 90 degrees. And just for reference, this turns into a cosine negative 90 degrees minus gamma. And cosine, when it has negative inside, will always be positive outside. I don't know if that really made sense, but let's try it to prove that. Let's say if I have an angle, what's a number we can use? A. No, we have a. Let's just say angle Z, and we take the negative of that. Note that it just goes to quadrant 4, and the function is still positive. So what this means is that even if we just remove this negative, this is the same. Nothing changes. So a cosine 90 degrees minus gamma. And let's do something else here. We have the z again, and we have, let me make that smaller. We have the z again. And if you remember this proof from last time, we do the same thing. So this is just equal to sine x. Oh my god, sine gamma. So this side is a times sine gamma. So let's write that in. Oops, I should stop doing that. Oh my god, I suck at erasing stuff. So this one is a sine gamma. Alright, so we have this side, and we want that to be squared, and we have this side left. So we already have b, so we just need this length. And as the other time, what we can do is divide it by a and multiply it by a again. So let's start. So this is our a term for the a squared, and this is our b squared term, and we're going to get c squared. So let's begin. This side, let's use this one again. So sine, we haven't done one with 180 yet, so let's actually try 180. That would be a bit more fun. So this side, let's get, so let's start this. So we have a cosine, since this one divided by that, of 180 degrees minus gamma. So let's try proving or finding another variation of this. So consider, this time we're not going to use a triangle. We're going to use a different method of proof, which is why I wanted to do 180 instead. Let's consider we have an angle. We're still going to use a triangle, but we're not going to use a triangle to capture the entire 180 minus gamma angle. So let's consider this as z. Oh my god, why does it keep switching? And so as stated, we want to make the hypotenuse 1. So let's get the coordinates of this point right here. This point is equal to this and that. So this is cosine. So cosine z, that's our x value. And then this side is this divided by that, and so that's sine z. If we draw an identical triangle just reflected over the axes, and note that this is 180 minus z, we get that, let me switch color, this angle, this line comes here. So we want to notice how these coordinates change. So these new coordinates will be, note that x is now negative while y is positive. So the same thing here, this is cosine of z, and then we have sine of z here. What this means is that whenever we have an angle z, if we do 180 minus z, the sine always stays consistent, while the cosines will change parities. Oh my god, that's a big eraser. So let's rewrite this as a cosine of, my bad, negative a cosine of just gamma. So now we have all our elements. So let's get to the algebra. This will turn in, I'm going to try to do this a bit faster since I'm taking a lot of time. Plus, so we have the first term squared, and the second term squared, which is a squared cosine squared gamma, and then 2ab, so that's minus 2ab cosine gamma. I think that's right. All right, so now we want to simplify this. So what we can do right now is take out, factor out the like terms. So let's take out a squared sine squared gamma plus cosine squared gamma. And if you remember in the cosine 2x section of the video, we actually finished proving that sine squared plus cosine squared equals 1. So that equals to 1. So this is just a squared plus b squared minus 2ab cosine y. And what this equals is, why did I square it? C squared. So if we move that here, we square root both sides. We get rid of the square and square root cancel. And we're left with this beautiful equation. Oh, what am I doing? Alright, now let us move on to the sine law. This one is a over sine a equals to b over sine b equals to c over sine c. I made that a little too big, so we're gonna draw everything else a bit smaller. So as mentioned, this triangle, oh, I did not mention that, my fault. This triangle can actually, you can take this part and unfold it in a sense and make it like that. So this is the other way to prove cosine law. However, for me, it's not as intuitive as we don't really get to the Pythagorean part of it. However, I will use this method for the sine law, just as stated earlier, for variety purposes. So let's get the triangle out. very sorry for the slow drawing. Oh my. There we go. So these two are, and here is H. So it doesn't really matter where you put A, B, or C. Well, it does matter where the angles are. So let's make the uppercase the sides. Am I doing this right? Yeah, A, all right. So let's make the uppercase the sides. I forgot which order I did it in. A, B, and C. And then let's make this angle A, let's make this angle B, this angle C. Remember, the angle of the side is always the opposite. So let's start. So let's just do sine, I don't know, let's A's first. So let's just do sine A. So sine A equals H over B. And we want to get rid of the discriminator. So let's do B sine A equals H. So we want to find something else that equals to H. I think this is the easiest one to prove, actually. So sine, it's the opposite. Sine B equals to H over A. It's just difficult to balance a lot of the more variables, since there's, I think, 7 of them. So note these two are the same. So B sine A equals A sine B. And we divide both sides by A, and then divide both sides by B. The A's cancel, the B's cancel, and then we just get a wonderful formula. So a question I usually have is, what about C? Like, what happens to C? Well, oh my god, all right. So C, in fact, also works, and we don't really have to prove it through this angle in particular. We can just show that if we move H to, let's say, here, we can do the same thing just by using C and B, and if we move it here, we can do the same thing with A and C. So this just works if you rotate the whole thing, and yeah, that's how we arrive at the sine law. And that is it for today's video, I think. Yes, that is everything that we have done so far. From these videos, from these proofs, what we can learn is that the hardest part of actually doing these proofs is thinking of the idea. If you were to give me a couple minutes just to come up with some of these diagrams, it would be really difficult for me to find a method. And I don't think I would, especially for maybe some of the harder ones today, like the initial one with the compound angle theorem. That one was pretty hard. However, just by memorizing some of these basic diagrams, you can derive them fairly easily. Both cosine and sine can be proven excuse my drawing. With this one, or this one. Both of them can, I'm pretty sure. And this is for the compound angles, so x plus y, or plus or minus y, and the sine and cosine law can be proven with either this one or this one. You just have to switch up the tactics a bit, I think. I'm actually not sure if this one can work for the sine. But if you want some practice, you can try using this method. I'm pretty sure it will work because it's a triangle at the end of the day. You can try it yourself to get the sine law from this diagram as homework if you want more practice. However, I'm pretty sure this one works for both. I've definitely seen cosine law proved with this. So out of the 4 diagrams, you only need to memorize 2, and then you would probably be able to conquer any of these identities on a test. So do not feel too intimidated, as it's not really too bad. Try memorizing all the examples just in case on the test you forgot one of them, you can use the other. If not, just get really used to one of them. And that is it for today. Thank you for watching, and I will try to post the second chemistry episode in the coming days, especially for the preparation of the exam. I want to try to get more material memorized, and also I will be trying to start a new series based on coding, just because it seems like a fun project that people can get into. Let me know what types of projects you would like to see, and I will try to see if I can get that done. And yeah.